Okay, now we'll go over edit and run a vehicle workflow. So if you locate the workflow in the workflow gallery and click on it, the edit and run workflow will load, and you can kind of see the main areas of it. There's a vehicle information panel here. There's an area which the powertrain will show up. And then there's a series of tabs here: files, parameters, signals, and plot. What I'll do is load a vehicle, or select a vehicle. So we click on select a vehicle. And you can see the list of vehicles will appear here in the tree. And you could click on a vehicle, and as you click on the vehicles, you can see a powertrain picture for the vehicle. So you have some information. Even when navigating the selection tree, you have the display name of the vehicle, where it is in the group, a description of it, the vehicle file name, which saves all the options, the files and parameters and model options that are selected in the user interface are saved in the A vehicle file. And then you have the powertrain picture here. You can navigate through the tree and find the other vehicle types, or you can do a search. One thing to keep in mind is that this demo is with the teaching version, so the complete set of vehicles isn't here. There's over 100 vehicles in the full version, but for this demo today we're using the teaching version, which has a reduced set of vehicles and files and models. So you can see the powertrain picture here, so you get a very good idea of sort of the vehicle powertrain that you're selecting, and we can see here that this is a power split configuration where you have two motors, a traction motor and a motor to control the engine speed, along with a planetary gear transmission. So we'll select this powertrain by clicking OK, and you'll see it load. So you have the information load in the vehicle information panel here. You see a picture of the powertrain loading here, and you also see the files tab being populated with all the files that define the vehicle. What I'll do is I'll just kind of collapse the tree so you could see sort of the top level architecture of the vehicle. And the top level architecture of the vehicle matches what you're seeing here in many cases with the powertrain picture. So if I click on the top level, you can see that there's a driver. You can see that there's the VPC, see the environment block. You have the vehicle propulsion controller, which is this block here. Then when you click on the vehicle propulsion controller, you can see underneath the VPA the different blocks. So you can see the engine here. There's an engine block. Mechanical accessories has a mechanical accessories block. The DC to DC boost converter is also there, along with motor 2 and the planetary gear, the traction motor, the torque coupling between the traction motor and the ring gear. There's a vehicle dynamics block here, the energy storage block, the 12 volt DC to DC converter, and then the electrical accessories. Underneath the vehicle dynamics block, you could also see the other components here for the vehicle dynamics. And if you click on that, you can clearly see the outline of the vehicle dynamics block, where you have the final drive, the wheels, and the chassis. One other thing to kind of note is that this layout of the powertrain also matches with the architecture in Simulink. So if I click on build in the ribbon here, it will create the Simulink diagram. So clicking on build will construct the Simulink diagram. We'll see MATLAB open, and we'll see the models added to the Simulink diagram. So MATLAB's opening. We could see the build process beginning. And it takes a moment to create the diagram. And what this shows is that the architecture that we see in the user interface is the same type of architecture that we see in Simulink. So there's the environment block. You could find the environment block here. The driver block has a corresponding driver block in the tree. The VPC has a corresponding block in the tree here. And then the powertrain, if you go into the VPA and underneath the VPA, you can see all the components here underneath the VPA. They also match with what's in the vehicle. And we could drill down and go within the engine, and you can see that the engine is composed of a controller block and a plant block. And you can also see that here, that if we go within the engine, you can see that there's a controller block and a plant block. So the representation you're seeing in the user interface matches closely to what you're seeing in Simulink. Now the different file types that you're choosing here, if we look at the configuration along with the model are the two file types that define the Simulink diagram. So this Simulink diagram here is defined by these two columns. The model exists on the lowest level. So that's where the user creates all their equations and algorithms are stored in this lowest level, which would be the model level. And that is a Simulink diagram, so I can right-click on it and open up the file, and we can view the file. So that will open up the file here. We'll see that there's a model, a corresponding Simulink model. Within that Simulink model are the various equations for calculating the results, say fuel economy from the vehicle, or fuel consumption from the vehicle, temperature of the engine, and other characteristics, torque output of the engine. So those equations reside within this Simulink model. Now there's also sort of this notion of architectures, and that's what we're seeing here. In this configuration file are the files that define the sort of the layout and the interconnections of those models. So with the powertrain itself has a configuration to define how many components are in the powertrain and how those components are connected. And that's this column here. So you can see that we have under the VPA, we have a split configuration that has in-wheel drive, because the wheels are contained within the vehicle dynamics block. So this architecture itself defines this level, but the number of wheels are actually defined within the vehicle dynamics block. So this architecture itself is agnostic to the number of wheels. And then it's stating that there's a power conditioner for the battery, a boost converter, and that there's a torque coupling for the motor. Now, one can go in here and look for new configurations. And as you go through the tree, you'll see the picture updates. So that gives you an idea of what type of VPA configuration or the layout of the components in the VPA configuration. So even before selecting the configuration, you have a pretty good idea of what blocks compose that configuration. So what we can do here is we could switch it. You could see that there's a torque coupling in this picture, and there's a boost converter here. I could just show how you can change the configuration by clicking OK, and then that goes through and updates the configuration. Now, to have this as a running version, there are a few files that would need to be changed in terms of pre-processing, because the architecture of the vehicle is different. So some of the VPA files for initializing the workspace, the M files themselves, would need to be changed. I won't go through all those, but I'll show here that by changing that configuration, this messages window is being used, and this sort of highlights the use of the messages window. You basically use the messages window to go through, and it informs you what sort of things you need to do to your vehicle to complete the vehicle. So because we changed the architecture, there are some files that have been changed that would need to be updated to make it work with this new version. So there are things here in the pre-processing category that would need to be updated. And I'll just show briefly, if you go to the pre-processing category, you can find, the equivalent files here, depending on the architecture. So you could do a search and find the files that are associated with, computing the mass of the vehicle. So you would drag and drop the mass, you would click OK, and the messages change. So you would work through the messages and select the correct files to remove all the messages. Let me move on. So I will actually go back for a moment, because what we'll do is we'll talk about the other file types in a little bit more detail. And what we'll do is we'll import, or I'll show you how to bring in your own model and your own initialization file to go through the import process. So what we'll do is we'll just close this for now. And I will go back to Edit and Run a Vehicle. And I will select the split vehicle. So just to kind of review the actions, you select split. I typed in split, I click OK. And this loads the original vehicle. So here we talked about configuration and model. The initialization files are the files that have all the initialization data for the model. So if you have a fuel rate map, that would be in an initialization file. If you have a maximum torque curve for the engine, that would be an initialization file. If you have an efficiency map for the electric motor, that would be something that would be an initialization file. Scaling files change the data that are being provided. So you might have a fuel rate map for your engine, but you want to scale that fuel rate map because you're assuming that there'll be technology improvements, say, into the future. And that's where you'd use a scaling file. You can also do the same thing, say, with power. If you have an engine of a certain power and you want to increase the power, you can scale it linearly, which would increase the fuel proportionally, or the fuel consumption proportionally, everywhere in the map. So those are some sort of basic assumptions that can be done. Pre-processing files come into play when you are taking data that appears in the initialization file and transforming it. So with the pre-processing files, you might be given a fuel rate map, but you want to take the fuel rate map and you want to transform it into an efficiency map. So you would use a pre-processing file for that type of computation. You might also be given something like a BSFC map, brake-specific fuel consumption, and you'd want to convert that into a efficiency map to do scaling. There's also cases too with plotting where you want to maybe have the map in terms of, instead of having fuel rate as a function of torque and speed, have it as a function of power and speed. So a pre-processing file would do that type of computation. Then you have post-processing files. With post-processing files, those run after a simulation. So the action while doing a simulation is basically the initialization, scaling, and pre-processing files run. The model is constructed and simulates, and then after the simulation is completed, the post-processing files run, which compute things such as energy for each component, efficiency for each component, and also add values to the HTML report that appears after a simulation and saved. Now, what I'll do first is I will save the vehicle with a different name. So we'll go here and we'll create a demo node in the group. We'll call the vehicle demo. We'll add demo to the description. And we'll save the file in the same location, but we'll append demo to the end. Then we'll click OK. You can see the information here is updated, where it is in the group is updated, description's updated, display name's updated. So some of that basic information is updated. What I'll also do is we'll add, so if you go to Windows Explorer and you go to the Amber folder, so Amber 2021, and you go to Libraries, what I'll do is I'll create a demo library here. So I'll just right click and create a folder. We'll call this folder Autonomy Demo. So we have this Autonomy Demo folder. Now what I'll do is I'll go to Autonomy and I'll go to the Edit a Project. So we're in the default project and I'll go to Edit, which has all the options for the project. So among the project settings, we'll go to Add Folder as Library. And I will add this demo folder. Click OK. And I'll promote it on the path up to the top so its files are found first. This is the order in which files are searched. So Autonomy Demo will be first on the path in MATLAB, and then any files in Autonomy Con, Autonomy Energy, and Autonomy Process, they'll be searched in that order. You could also change the desktop mode, so I'll put it in desktop mode so we have the full desktop that appears. I'll click Save and Close. And we'll just say no for saving power split. MATLAB will reopen. Click OK. One thing I'll do is I will close this workflow. So I'll close it, then we'll reopen it to make sure that the new project is on the path. So I'll go to Workflows, I'll go to Edit and Run, and then we'll load that vehicle. And here you can see that under 3 Demo, you can see that there's a demo PHEV. So that was saved in that location, so we click OK. And then that loads. And now what we could do is we could make modifications and then save our changes to this demo vehicle. We'll also import some new models and save those to the demo library. So that was one of the reasons why I was doing that. So what we'll look at here is how to add your own models. So what we'll do is we'll go to the electrical accessories and we'll go to the plant. And we will clone the plant. So the electrical accessories has a Simulink model, and there's a corresponding file that's used by the user interface called a metadata file that has additional information about the SLX file. So I can open up the original file, and we could look at it, which we've seen similar before for the engine. It's the same type of idea. You have a Simulink subsystem with a given set of inputs, a given set of outputs. And you can see that there's a metadata file, which I won't go into too much detail. It's sufficient to say that it's an XML file that has information about those inputs and outputs. Now what we'll do is we'll do a clone. So what a clone will do is it will make a copy of the Simulink model, and it will make a copy of the A model file or metadata file. And then what we can go in is we could go in and modify the Simulink file. So we'll do a clone. And the same idea here, what we'll do is we'll remove the date timestamp at the end, and we'll just call it demo. We'll remove some of the text at the beginning here, and we'll call this demo. And then in terms of the location, there are different options. So instead of saving it in the project folder, what we'll do is we'll save it in this library autonomy demo. So the library we just added, we'll save it there. And at the end, what I'll do is I will append demo to the end of the file. And we'll click clone. And we'll say yes. I want to create it. So now we have this demo file here. And we'll do the same thing for the M file. We'll go to the M file, and I'll show you the M file. If we open up the original file, it's the same idea. There's a MATLAB file, that's the M file. It has the initialization data for the Simulink model. There's a corresponding metadata file that has information about the M file, such as the input and output parameters, description, display names, compatibility to other Simulink models. So that information is stored in the metadata file. But what we'll do is we'll do a clone. So that will clone the M file, and it will clone the metadata file. So I'll click clone. We'll do the same thing. We'll remove the number at the end for date time. We'll just put demo. We'll remove from the display name the text in front. We'll just put demo. And then we'll choose a folder. We'll choose the Autonomie demo folder, or we'll choose a folder under Autonomie demo. And it's just being saved in the general init folder in there. So we'll just click clone. And we'll just say yes, create the directory. And then that will clone it. So now we have both the cloned Simulink model and the cloned initialization file. I'll just close this. Now what I'll do is I'll open up the model and we'll modify the SLX file, or modify the model. So we'll say open file, and we'll give a moment for MATLAB to start. MATLAB starts and the model will open. So we can see the Simulink model here. What I'll do is I'll modify this model. We'll just make a small change to it. What I'll do in Simulink is I will make an additional parameter, and we'll call this power demo. I'll just copy the text. We'll click OK. I'll click sum, and I'll click on the Simulink canvas and click sum, and I'll add a summer, and then I'll just make the connections. I'll grab the connection at the end of this constant block, connect it to the summer, and then I'll connect the summer, the output of the original constant block to the input of the summer, and the output of our new demo constant block to the input of the summer. And that will be our modification that we're making to the model. Same idea follows through with any modifications you would want to make. You can go through and basically change anything in this model. It's the starting point. If you want it to run in a default vehicle in Autonomie and be compatible with the other powertrain components within Autonomie, we suggest following the same sort of input and output interface, but you can modify the internals of the block as long as the interface is the same. If you're using your own models with it, then the interface could also change too. So we'll save this, and I'll close it. And now we'll also open up the M file. So I'll click open here, right click. These are all right clicks to open up the context menu. So I'll paste the parameter here and give it a value of 100 and save it. Now one thing that we do have to do is we have to resync the models. So we've made changes, but the changes aren't automatically recognized by Amber to regenerate the metadata file. So we have to tell it, okay, I'm ready, let's regenerate the metadata file. So we have to do a resync. So what the resync will do is it will read all the parameters in the Simulink file, in that SLX file. It'll look at all the input and output ports of that subsystem block, and it will add that information back to the metadata file. So it's doing the resync here. It's resyncing it. It's getting all the default signal and parameter information. It does have an internal dictionary, so if it recognizes the parameter or the signal as being a signal or parameter that's already in Autonomie, that has a description and display name and all the units, all that information will be read in from that dictionary file. So we modified the parameters. So we go to parameters here for the model, and you can see it's here. What I'll do is I'll state that it's power, and it's in watts, so we click save. Then the same thing we have to do with the M file. We have to resync the M file, so we do a resync here. And we go to parameters because it's a new parameter. These are input parameters. We want to go to output parameters. You can see that the parameter is here. So I'll also adjust it. So this information is all saved in that metadata file. So I'll select power, it knows that it's in watts. And you can make a parameter overwritable. We'll talk about overwritable parameters soon on the parameters tab. That just means that when you select a parameter as overwritable, it will show up in the user interface as a value that you can overwrite and give a new value different than what's in the M file, and that new value will be saved in the A vehicle file. So I'll save this. Now that it's been resynced, it's ready. And what we'll do is we'll just save this vehicle. So we'll do a save. We'll save it. We'll say yes, overwrite. Now that it's been saved, we could also rebuild the vehicle. So I'll go to build, and I'll build the vehicle. So now we'll reconstruct the vehicle with our new Simulink model. So we'll construct it with this demo Simulink model. So I can go into Simulink, and we know that it's the electrical accessory block. So electrical accessory. We navigate to the electrical accessory block here, and we can see that it's using the demo model. The name is right here. Select plant cons power bolt in demo. Double click on that block, and the actual model that you define is within this block here. There's some work that's done to aggregate signals onto buses and then separate the signals and send them, select a signal on input and aggregate signals together and put them onto buses as an output. So there's sort of a standard interface for blocks within Simulink. So every SLX file that's defined as a model will be used by default in a construction like this, where you have a parameter selection block to select things from the bus and a parameter out block to put things onto the bus. You might ask, well, what defines the buses? What defines input buses and output buses? Those input and output buses are assigned to connections based on the configuration files. So it's the configuration files that kind of define the signal flow architecture of the model. And it's these lowest level terminating blocks that actually put signals onto those buses. So we'll go into this model, and you can see the parameter has been added here. You can also do an eval and evaluate the parameters, and you can see the parameters are evaluated and in the workspace. So accessories electrical is select.plant because it's in the plant block, .init because it's a value in the initialization file column, and you can see the power demo value there. Okay, so that kind of shows how you would import a new model or a new M file. It's the same process for scaling and pre-processing and post-processing files. Now let's go to the parameters tab. So we can go to the Parameters tab here. And this is a very similar idea to what was in the Run a Vehicle video. It's the same sort of idea or notion you have here. We start out with all the overwritten parameters. So these are all the parameters that are defined in this A vehicle file that can be overwritten. You don't have to show all those. You can have the overwritable parameters shown. And again, the overwritable parameters are all the parameters that are marked as overwritable in the M files and the preprocessing files. So those checkboxes that you would check in the metadata editor to enable overwriting, if any of those parameters have their checkbox checked, they appear in this table. And you'll see that the values don't appear for all the overwritable values. It's because they're not yet in the workspace. So if I click eval, it will evaluate and then load all those default parameters. You can customize this grid also, so there are cases where you might have a favorite set of parameters. So oftentimes parameters such as engine power are of interest, chassis coefficient of drag are of interest, frontal area. You might be interested in the rolling resistance. So you have rolling resistance coefficient 1, coefficient 2. There are higher order coefficients, 3 and 4, but those are oftentimes 0 in the default vehicles in Autonomie. There's also the wheel radius. Other values of interest could be the electrical accessory power, perhaps the demo power, which we just added, could be added. And there's also another parameter that, we could also do final drive ratio. And then finally, I will add one more parameter, the vehicle mass. So there's two ways the vehicle mass is determined for a vehicle in Autonomie. By default, all the vehicles in Autonomie, all the default vehicles, whether it's the teaching version or the full version, all those vehicles have an overwritten mass or a mass set in the A vehicle file. So that value will be the one that's used. This value doesn't have to be used. If that value is not there and it's not overwritten in the vehicle, then what happens is the pre-processing files, mass pre-processing files, you can identify them because they all have mass in their name, are used to calculate the component masses. So you'll see that. You'll see motor mass pre-proc. You'll see chassis mass pre-proc. Those are the files that are used to calculate the individual system masses, and then the VPA has one file to calculate the total mass of the vehicle. So that's another way that the mass can be calculated. So I'll do an eval, and then you'll see that we have the latest values here. Now we could save this as a default parameter list, or we could save it as a parameter list. I mean, you could just save it. Let's save it as you could just save it as a parameter list and then load it back later. There are other cases too. So if you start with the default parameter list, you could check this and then save it as a default parameter list. If that's done, then by default, the next time you load the edit and run a vehicle workflow and load a vehicle, any vehicle, this will be the default set of parameters. So in some ways you can have specific lists of parameters. Maybe you have a set of parameters for the plants, maybe you have a set of parameters for the controllers. So you can have different parameter lists that you can load and save from here. The other option too is to have a default set And if you don't set the default set, then by default it's going to use all the overwritten parameters in the vehicle. Sometimes there's quite a few overwritten parameters, so maybe it's nice to see just the set that you're interested in. So here we could just, do things like overwrite the vehicle mass. Just type in a new value. You can update the power of the engine. Typing a new value there. If you right click, oftentimes you could restore the original value. If you lose track of the original value, you could restore it. So we'll keep it at 100 kilowatts. There are other things. You could remove rows, so you just right click and then remove a row. You can do that. The table too is searchable, so you can search for parameters that you're interested in. It's helpful when you have the overwritable parameters because it's such a large table of parameters. It's helpful to have search enabled. The system path gives you an idea of where the parameter appears in the vehicle. So you have an idea that, okay, the wheel plant init coefficient roll 1 would be in the vehicle, would be under the VPA, the vehicle dynamics block, the wheel system, and then the plant. So that kind of gives you an idea of where you can find it in the vehicle. Specifically, we could look for it in the Simulink, but we could also just find it under the wheel and then plant. So it matches the path here. You have vehicle as the top level, then you're under VPA, and then under the VPA you have wheel, and then it would be in the wheel file here that you'd have it. So you can right click on it and say open file. And you can see here the coefficient rolling 1, coefficient rolling 2. So the paths here give you an idea of where they are in the vehicle. The other thing to note too is you go to the Signals tab. The Signals tab shows you the input and output signals of a block in Simulink. So I could type in ENG /plant. And you can see that there are 2 input signals. I could do another search. We can see that there's 2 input signals on the engine plant. So we go back to Simulink and we go to the engine and we go to the plant, you can see that there's these 2 input signals. This table is just for signals. There's also this notion of effort and flow, which are the physical connections between the components. So if you go back up to the top here, you can see that these are the effort and flows. We're trying to maintain a bond graph sort of methodology. So we're sending out torque, and then we're feeding back a flow, which would be speed. So that's following that sort of bond graph methodology. So what we're really showing in the Signals tab are the signals coming in on a bus and the signals leaving. So signals correspond to the bus creators and bus selectors, which are in these blocks and are constructed automatically for you. Not all the signals are put onto a bus. There's a minimization procedure that goes on to make the diagram run a little bit faster. We don't put every signal onto the bus, only the signals that are actually being consumed somewhere. So an output is only put on the bus by default if it's actually seen to be used somewhere else as an input. Same here, you could look at the outputs for the engine. So the outputs for the engine appear here. So we go to the engine, we go to the plant, and I was just showing it. You can see all the outputs coming from the engine. So those match up. So what you're seeing here in the grid is matching up to what appears in here. So you'd have an engine on, there's an O2, exhaust gas flow is here. So if you could go down this, through this list and kind of see and match up the inputs and outputs. They are also saved to the workspace, so that's what this is indicating here, is if a signal is saved to the workspace. That's something else that you could turn on and off for individual signals. By default, they're all turned on to save to the workspace, so that's why you see these 2 workspace blocks here. because that's indicating that those signals are being saved to the workspace and appear in the results file. So if you want to see where any of the signals are being saved and how they're getting into the results file, that data.mat file at the end of the simulation, it's from these parameter selection blocks. So that's true for the engine, it's also true for any of the other blocks. If we go into motor, you'll also see the same type of block. You have the plants, the actual Simulink model that a user would create, and then you have the block in which the signals are saved out to the workspace. Then you have plots. I'll just do a quick plot here. If you go to engine.plant, you can find all the engine plots. Let me just close this. Just clear MATLAB. And then these plots evaluate in the workspace. So we can look at the efficiency map, and we'll look at the torque versus speed. Now we haven't actually run a simulation yet, so we're going to plot the efficiency map for the engine and just the operating points. So we'll plot here. It's fine because right now there are no operating points. So you could see the efficiency map for the engine. You can go to parameters too, and this is sort of where it's helpful if we wanted to boost the engine power. Just see how it affects the engine map. You can increase the engine power. You just do an eval. We'll go to plot. And then I'll make the same plot. And you can see it opens up another plot. And you can see the power has changed, so, or the amount of torque. So here you see the original torque, and then we boosted it, increased the power, so we've scaled up the torque of the engine. So now you're around 300 Newton meters, and before you were around 200 Newton meters. So you can make changes or scale the engine. You could run different scaling files and see what effect they have on the engine map before you run the simulation. And now we'll just run, actually before running a quick simulation, there's a couple of things still I could talk about. One is that when you're adding files to the vehicle and creating new files or importing your own architecture with their own files, it's somewhat useful to be able to debug the evaluation order. And we suggest debugging the evaluation order by going to create eval file, clicking on that, and that generates a file for the entire vehicle. So all the M files that you have for your vehicle are sorted based on their inputs and outputs. So they're metadata files that record the inputs and outputs of your file. And those inputs and outputs are used to determine what order those files should be evaluated in. If you want to see what order they're being evaluated in, you can generate this one M file for the entire vehicle. There's also sometimes advantages to that. You might see sometimes there are clears that occur in M files where a user will, put a clear into an M file that clears the workspace. There are times where people will add extra fields or remove fields in M files. So it's kind of useful to be able to go through and put a breakpoint in the eval order and see exactly what's going on. There's also this debug vehicle. So debug vehicle basically just creates the Simulink model. So here we'll choose a cycle. Sometimes you may want to create a diagram, construct a diagram, make modifications to the diagram, run it, make some more modifications, run it, make more modifications and run it, and you're in this tight loop of kind of developing your model. Once you finish developing your model, you can always go back and re-import everything, but this kind of helps you get your data into the workspace, your model into the workspace, and then allows you to kind of run everything. Sometimes there's data already in the workspace, so it's good to do a clear first. Let me do that again. We'll do back to debug vehicle, we'll do the UDDS, drag and drop it, and then click OK. It's used to be able to have the workspace initialized, have the vehicle ready to go, and be able to run that simulation and be able to kind of see what your vehicle is doing. And this is just kind of a quick way to get it up and running and being able to debug it. So you can see that it's running now. So we'll close that. So those are a couple of extra features that are sort of nice to be able to use. So we'll go to select a process, and we'll just do an ECE cycle. And again, you can increase the number of repetitions on the cycle if you wanted to run more copies of the same cycle. You can see the plot updates. You can do SOC correction. So turning on an SOC correction can be done here by checking the box. There's also a Parametric Study option that you can run. So if you go to Parametric Study, we'll just talk about that briefly. Parametric Study is when you want to sweep a parameter. So you could sweep, say, so you can overwrite the parameter as we did, the engine power, and that creates a new default value. So wherever you see default, that would be whatever the default value currently is. But you can always add a range of values, increment by the number of points. We could say that we want to sweep, now this is in watts, so we want to sweep from 100,000 to maybe 130,000, and we'll do 4 values. And then we'll remove this original default. Move value 1, there you go. So you could see, okay, we're going to sweep the engine powers. Now maybe you want to sweep also vehicle mass. So there's two options here that can be done. You can sweep it, you could sweep engine power and vehicle mass at the same time. So what you're really doing here is you're varying both at the same time. So you're only going to run 4 values. And these are essentially vectors of values that you're changing. So you're going to change the engine power to 100,000 watts, and you're also going to change the vehicle mass to 1,000 kilograms. Then on the next simulation run, you're going to be at 110 kilowatts and 1,200 kilograms, and then 120 kilowatts, and then 1,300 kilograms. The other way that you could do the sweep is you could take the product of the two rows by dragging it into the empty space, not dragging it onto this row, but dragging and dropping it into the empty space. And then you can see here that we can add a range. We can increment by the number of points. And we could go from 1,000, 1,500, and we could do 6 points. And you'll see that it'll do, 4. I have the default value since I appended it. It's appending it, so we'll remove the first value. So we'll have 4 by 6 or 24 values. So if we go out, you'll see the 24 values, and you can see the values it'll sweep in the table. So if you ran it this way, you would have 24 simulation runs. So we'll go back to Process Selector. We'll unclick Parametric Study because we don't want to run it in this case. We'll just do a quick run. Then we'll go to Run Simulation. One thing to note is you can go here and to generate and open a run file. If you click Launch, it will just say yes because we're not running a parametric study. You generate this run file. You can see all the options that you were choosing in the user interface are saved again to an XML file. So that's oftentimes a lot of the work that's being done. You have the MATLAB files and you have these corresponding XML files. In many cases, you have XML files that have the options that you're selecting in the user interface. So here we're going to just run that file. So we're going to hit launch. So what it'll do is it will generate that XML file I just showed you, pass it to an M file, and then that M file will read those options in the XML file and start running the simulation. So we click launch, we click OK or yes, because we're not going to run the parametric study. And then the simulation is running. The simulation will complete. You can see we had the 2 cycles selected, so we'll run the 2 cycles. Then again, you have results here, you have plots, and this is in line for if you had multiple simulation runs. If we ran that parametric study and you dragged and dropped any signal here, you would see the results for all those simulation runs, not just the current one. If you want to look at individual simulation runs, you'd click Open here. And that will open, and you'll see the HTML report. You'll see for the HTML report, there's also an energy balance diagram for each component. So you can see the efficiency of each component. You can see the average efficiency and also the efficiency when working in the forward direction. So for a motor, that's when electrical energy is turned into mechanical energy. And then in the reverse direction, where you're taking the mechanical energy and turning it back into electrical. So one way is propelling, the other one is regenerating. And so there's an average efficiency in both directions. Then the efficiency values are in the table. There are also maps that are saved with figures. So you have a figure saved with the energy density and where you operated the most in the map according to energy density, Willen's plot. So there's interesting information that's saved in that HTML report. You could do plotting. So here you're doing plotting only on whatever simulation result is loaded. So we're doing plotting only on that one. So we could plot engine torque, plot it on the same graph. You could plot engine speed, drag and drop it there. And you could double click on the plot and we'll open it in MATLAB. So you could copy and paste that. And then again, there's the predefined plots. So if you wanted to see the same plot from before, we can plot the engine. We could also filter here on engine, so you could plot the operating points, torque and speed operating points. You can see that. So have the torque and speed operating points. You could also see that same energy density plot that you see in the HTML report. So that was by power. We want to do it by torque and speed. So there are a few options. That sort of goes back to what I was saying too about the pre-processing files. Is the type of transformation we're looking at. In the initialization file for the engine, you're given a fuel rate map. But then in the results, we want to plot an efficiency map in terms of torque and speed. But then we also want to plot an efficiency map sometimes in terms of power and speed. So it's that pre-processing file that takes the fuel rate map and produces these two additional maps that can be used both for plotting and, in the case of the efficiency map, for scaling. If you want to go to the results folder, go back to summary, you click the open result folder here. And it depends on which result you have selected. So if you had multiple results, whichever column was selected, that's the one you're opening. So you can open it here, and you see the different file types. You can see where they're being saved to. It's in the current version projects. We're using the default project where we added that demo library. But then you're under results, and then there's a date timestamp folder, and then the name of the cycle. Here's the HTML report that appears in the user interface, same report. There's a vehicle save that you can use to rerun your simulation. So this is all the options and all the changes that you made in the user interface. There's your Simulink diagram, which can be opened from here. You can open up your Simulink model very easily from the user interface. You can also load your data into the MATLAB workspace. So if you wanted to go into MATLAB and investigate the data, run your own M files, you can do that very easily here. They're just saved as arrays. And the time-based values all have this underscore simu on them, so you could plot. So the signals that you see appearing in the user interface that you're dragging and dropping, those are the same signals in MATLAB. So back to that results folder, you have data in it that has just the initialization values, no results. So you can use that to reinitialize the workspace if you wanted to. I could clear all here. Let me close this. And if I drag and drop the data in it, you can see it's just the initialization data. If I drag and drop the data.mat, you can see that it's not only the initialization data, but it's also the underscore simu. So it's a time-based data, which appears in these time-based vectors or arrays. They're just arrays of numbers, doubles. There's also these additional files. Again, it sort of goes back to the one initialization file for the entire vehicle. There's an initialization file for the vehicle that's also saved out here, and there's also an a post-processing file that's saved out for the entire vehicle. So if you want to see what order your M files are being evaluated in, you can do that from here. So we could look at those files briefly. If we navigate to the results, I can open up this file, and you can see here it's the same sort of type of thing where you're given a default initialization file that has all the files as they were evaluated in the workspace to run your simulation. But then there's also a post-processing file, so same idea, but here you have all the post-processing files that are in the user interface and saved to that A-vehicle file. So that gives an overview of the edit and run a vehicle workflow. So you can edit and run a vehicle all in one action. There's the edit a vehicle workflow, which does the same thing. If you just want to edit a vehicle, it's really focused on just editing the vehicle. It's the first say tab here that you would have. So it's an option either way. If you want to edit and run, you can use edit and run. If you just want to edit a vehicle, just use edit a vehicle. But even with edit and run, you can still save your vehicle. So you could load this workflow. You're still able to go in and save the vehicle. So this is always a good option. So that completes the overview for edit and run a vehicle.